Hello and welcome back, statisticians. We're continuing our easy peasy chapter 5. We're going to be talking about the binomial distribution. And if you know what bi means, it means two. So binomial distributions have two options. So we're going to find the exact probability for x successes in n trial of a binomial experiment using a formula, a table, or your handy dandy, your ever useful graphing calculator. So let's get started with the very first key concept. Binomial probability distributions allow us to deal with circumstances in which the outcomes belong to two relevant categories, such as acceptable or defective, survived or died, yes or no, do you have the virus, do you not have the virus, that kind of thing. So we're going to be talking about the probability distribution results, and they have to meet some requirements. First off, it has to have a fixed number of trials, we call n. The trials have to be independent. The outcome of any individual trial does not affect the probabilities of the other trials, and each trial must have all outcomes classified into two and only two categories, commonly referred to as success and failure. The probability of a success remains the same in all of the trials. So let's give two examples of a binomial experiment where a situation only has two outcomes. So a coin toss, heads or tails. A baby is a boy or a girl. You heard about the two babies that were in the nursery, didn't you? There was a little boy baby and a little girl baby. And the little boy baby said to the little girl baby, "Hey, I'm a boy and you're a girl." And she goes, "How do you know that?" And he goes, "Look down. See what I've got that you don't?" And she goes, "What?" He says, "Well, look down. I've got blue booties." I know you're expecting something different there, but he had blue booties. Okay, so let's talk about a binomial experiment where a situation has multiple outcomes, but these outcomes can be reduced to two. For example, your medical treatment. Is it effective or not effective? They could talk about how much it's, like if you're doing chemotherapy, it shrank the tumor so much percent, but basically, is it working or is it not working? Part B, blood pressure. You've got this gauge here, but you know whether it's normal or abnormal for blood pressure. So you can take some situations and make them into binomial distributions. For example, if you were talking about a multiple choice test, you'd say you could have a correct answer being success and an incorrect answer being failure. Describe the following notation in a binomial distribution. So first off, P of S is the probability of success, which I hope is highly probable for you guys. Probability P of F stands for probability of failure, and P equals the numerical probability of success. So you'd say P of, like two tails, equals some number. So Q is the numerical probability of failure, thus this is success, this is failure. They're complements. P of S equals P, and probability of failure is going to be 1 minus P, which equals Q. So if you've got 20% success, let's say, then the probability of failure would be 1 minus that 20%, or 80%, or 0.8. That's their complements. N stands for the number of trials, and X is the number of successes that you seek in so many trials. The hard part of this lesson is being able to pick out these P, Q, N, and X from your given information. If you can get the knack of that, this is gonna be easy breezy. So also remember that the number of successes has to be between 0 and n, because you can only have a total number of n trials. Also, X equals 0, 1, 2, 3, all the way up. It can be any of those. Method 1, dun dun dun, the probability formula. So the probability of x is n factorial over n minus x factorial, times p to the x times q to the n minus x. This should look a little familiar. It's a combination. So remember, n is the number of trials, x is the number of successes. You already have these written down on your paper. It's a matter of being able to manipulate the formula. You have to pick the numbers out of your given information and plug them into the formula correctly. It isn't hard. Can you use a formula card on the test? Absolutely. So let's look at the first one. Coin toss 3 times. Find the probability of getting exactly 2 heads. The way you have done this before is by looking at the sample space. So here's the sample space. HHH, HHT, HTH, and so on. And notice the ones that are in purple, those are 2 heads. Better than 1. And there's 3 of them out of 8. So right from the sample space, it's easy to see that the probability of getting 2 heads is 0.375. Now this is a simplified example. The reason you need the binomial theorem and all that is you might have 100 trials and you need to know the probability for that. Well, you can't write all this out 100 times, so that would make the sample space very, very large. So we need something else. So we're doing a simple one just to kind of see what it is. First, does it meet our requirements? There's a fixed number of trials. There's 3. That's going to be your n. There are only 2 outcomes for each trial, heads or tails. That's the binomial part of it. The outcomes are independent of one another. One toss does not affect the next toss. And the probability of success remains the same, 1/2 in each case. So each case has the same probability. In this case, your n is 3. That's the number of trials. Your x is 2 because there's 2. You're trying. The probability of success is getting 2 heads. Probability of achieving a head is 1/2, and q would be 1 minus 1/2, which is 1/2. Then once you decide this, it is so easy because you can just plug it into the formula. 3 factorial, 3 minus 2 factorial, 2 factorial, and so on. If you do all this, you'll end up with 3/8 or 0.375, which we obtained using the sample space. But this was just an example to show you that yes, it does work. It's used for more complex things. So let's look at this next one. A survey found that 1 out of 5 Americans, when you see that 1 out of 5, it should clue you in that is a probability. That's why I have it in green. Americans say that he or she has visited the doctor in any given month. If 10 people are selected, they'll say sample, they'll say you selected or something like that. That's your trials. That's the n, 10 people. Find the probability that exactly 3 will have visited the doctor last month. 3 is your success. X will be 3. So first determine if it meets our 4 requirements. So number 1, there's a fixed number of trials. Yes, that is going to be 10. That's our n. Then, if so, how many? 10. We did that already. Are there any outcomes for each trial? Yes. There's only 2. Either they visited the doctor or they didn't. Are the outcomes independent? Yes. Somebody visiting the doctor is in no way affects if somebody else visits the doctor. Is the probability of success the same in each? Yes. Either they did or they didn't. It's 1 out of 5 is the probability for each case. So that's your p, little p. If so, what's the probability of success? 1/5, 1 out of 5. You could also put 0.2 if you prefer. Exactly 3, like I said, that's your x. That's your number, your success. The probability of exactly 3, that's the x. So in this case, n is going to be 10, x is going to be 3, p is going to be 1/5, and q is going to be 4/5. Let's plug it and chug it. 10 factorial over 7 factorial times 3 factorial, 1/5 to the 3rd, 4/5 to the 7th. So bada boom, bada bing. When you get that done, probability that exactly 3 people visited the doctor will be 0.201. Next one, survey from teenage research found that 30% of teenage consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. Now you may remember, at least 3, we always did the 1 minus, but in this case we're not going to do that. I'm going to do this a second way. When you see 30%, that's a probability. 5 teenagers are selected. That's your number of trials. At least 3 or 3 or more. So first determine if this situation meets the 4 requirements of a binomial experiment. Number 1, there's a fixed number of trials. 5. Are there outcomes for each? Yes. Are the outcomes independent? Yes. Is the probability of success the same in each case? Yes. That's the 30%. What's the probability? 0.3, which is 30%. In this case, n equals 5, And X has to be 3, 4, or 5 because there's only 5 people selected. That's your number of trials. So at least 3 means you have to do it for 3, 4, and 5. You're going to have to do 3 of them. Oh joy. So P equals 0.3, Q equals 1 minus 0.3 to get the 0.7. So to find the probability that at least 3 have part-time jobs, it's necessary to find the individual probabilities for 3, 4, or 5, then add them up. So substituting them into the formula, we know we've got n equals 5, and that's brought forward. So plug and chug. Here's where your x goes, n factorial, n minus x factorial, and so on. So if you plug all those in, you get 0.132. Then you do P of 4. There's how the formula changes. Notice 2 and 3, 1 and 4. This is 4, this is 1. You get 0.028. And then the third one, 5 over 5 factorial. So those cancel out. You get 0.3 to the 5th, 0.7 to the 0. Remember, anything to the 0 power is 1. So you get 0.002. Sum them up, and you'll get your final answer of 0.162. Probability that at least 3 teenagers have part-time jobs. All right. Computing probabilities by using the binomial formula can be time-consuming. So they have tables to kind of hurry us along. And the new modern world, we have graphing calculators that have them built in. But we're going to do these next ones using a table. And I want you to get your book, you might need to pause it, and turn to page 756. That's where these tables are, because you're going to have to do one on your own where you're using the tables to find these probabilities. So let's look at this guy, 518. Here's our example. Solve the problem in example 515 by using the table, page 756, table B. When using the table, you only need the values n, x, and p. Very nice. So this is kind of a mock-up of what the table looks like. Since n equals 3, we go down this far left column to 3. And x equals 2, so from 3 you got 0, 1, 2, 3. Notice how x is between 0 and 3, and it goes up by whole numbers. So x is 2, so that's here. And probability, the little p, is 0.5. Now up along here there's a p on the top, and over here is 0.5, so we'll go over from 2 to that column, and we get our probability, 0.375. That's pretty easy with our tables. I'm going to have you do the next one. Reported that 5% of Americans are afraid of being alone in a house at night if a random sample of 20 is selected, yada, yada, yada. Find the probability. There are exactly 5 people in the sample who are afraid of being alone at night. Are you afraid of the dark? So here's what I know. N is 20. That's our sample. X equals 5 because that's how many we're looking for. That's our success. And probability is 0.05. So from the table, one gets a probability of. You've got to find that one. You might want to pause it and then write that in your notes real quick while you've got your book open. Pause. Okay, there are at most 3 people in the sample who are afraid of being alone at night. Well, this comes into handy because we can do at most 3 means a 0, 1, 2, or 3, and we can use our table. Under n equals 20, we're going to look up the probability of 0, 1, 2, or 3. And if you look it up, probability of 0 is 0.358, 0.377, 0.189, and 0.06. So looking those up on your table, you'll add them up, and bada boom, you get 0.984. So let's look at the next part of this problem. What's the probability that there are at least 3 people in the sample who are afraid of being alone at night? At least 3 means bigger than 3, so 3 all the way up to 20. That could take a little time to add those up, so it can best be solved by using the rule of complementary events. That is, the probability of at least 3 people is 1 minus the probability of 2 or fewer. These are complements. We already did this one. So the probability of 1 minus p of 0 plus p of 1 plus p of 2, which we just found, we're going to end up with 0.076. I'm going to have you try example 5-20 on your own. Need to determine what n, p, and x are and find that probability.